this video, we start to see the instruction code of the SCOT CPU, in particular the ALU instruction. We see the control logic to drive the ALU instruction. This video is the simulation part of the theoretical video instruction code ALU instruction of the How Computers Work Building SCOT CPU YouTube playlist. The link to the playlist and the CircuitVerse link are in the description. Here we see the instruction code of the SCOT CPU. In particular, we see the ALU instruction. We have 8-bit instructions, and the first bit, so the most significant bit, if this bit is at 1, like in this case, we have an ALU instruction. If this bit is 0, we have another kind of instruction we see in next videos. So here we see just the ALU instruction. So the first bit is at 1. The second, third, and fourth bit are the opcode, which determine the kind of operation the ALU will perform. So in this case we have a 000, and in this case we are asking to the ALU for an add operation. If we put here a 1, so we have a 001 as opcode, so we are asking for a shift left, or if we put here 110, we are asking for an XOR operation. The last 4 bits are dedicated to the registers, in particular 2-bit for one register, other 2-bit for the other register, because in the ALU we can have 2 operands in some operation, for example in the add operation. So with opcode 000 we have 2 operands, and we dedicate 2-bit to choose the 2 register containing the byte we want to transform with our operation. We call it reg A and reg B. Of course, reg A and reg B are composed by the same 4 registers we have in the SCOT CPU, so reg 0, 1, 2, and 3. So basically, this opcode means add reg A to reg B. So we can write our low-level language, add RA to RB, and put a result in RB. So in particular it means add the content of register 0 to the content of the register 0 itself, and put the result in register 0. But of course we can do something different, like here. This instruction means basically add the content of register 2 to register 0 and put the result in register 0. So you see we have a low-level language more readable and understandable than the bits, and we take the content of reg A, we perform the instruction, and we put always the content in reg B. This register can be the same, so we can perform the operation always with the same register, because we can take the content of register 0 and then put the result in register 0 as we saw, but we always write in register B. There are some operations that needs just one operand, like the NOT operation, for example. So let's see, for example, the NOT operation is the opcode is 011, so 1, the first bit is for the ALU instruction, 011 is the NOT operation. So in this case, our instruction is note the content of register 2 and put the result in register 0. Or we can write XOR operation. So in the XOR operation, this is the opcode, and here we can change in this way. So this means XOR the content of register 2 and put the result in register 3. So these are the ALU instructions. Is an instruction code quite easy. And now let's see the connection we have to do in order to make possible the execution of this instruction. So let's see how to connect the instruction register in order to make possible the ALU instruction. We start from the instruction register, you see here. Here, this logic is to control the opcode, so to select the right operation in the ALU. You see these 3 inputs and gate are connected with the first 4 bits of the instruction register, and the last 4 bits, 4th, 5th, and 6th and 7th, are connected to this logic here. And this logic is used to select the right register. You see here the 6th and 7th, so reg B is connected to on the right to this logic and on the left to this other logic. On the left we create the enable pulse, and on the right we create the set pulse. As we saw before, we need to give a set pulse to reg B in order to acquire the result of the ALU instruction, but we also need to give an enable pulse to reg B. So here we have that the bits 6 and 7 are connected to this logic to drive the set of the register 0, 1, 2, 3 and to drive the enable of register 0, 1, 2, 3. And the bits 4 and 5 are connected to this logic here. This is reg A, which is connected, of course, with the same wire 0, 1, 2, 3 driving the enable pulse of the registers. This logic is basically a decoder, 2 to 4 decoder through which we select the right register. So in our case we see our instruction code is an ALU instruction because the first bit is at 1. We have 000, so it is an add instruction, and we ask to add the content of register 0 to the content of register 1. So reg A is 0, reg B is 1, and so we have to put a result in reg 1. So we acquire this code. And so you see reg B is 1, and you see that the line 1 is at 1, the other line is at 0, so this AND gate is connected to reg 1, so we select the register 1. The other 2 inputs are of course clock E, so clock enable, because we have to give the enable pulse in the right moment, and the other input is the right step, because we have to put the byte of the bus in the right step. The same here. This is reg A, and in our case we select the first register, so register 0, as you see is at high the 0 line, and the other input of this AND gate as the clock E and the right step when we want to put reg A on the bus. Here we created the set pulse, we choose the first register, so register 1, and this is the clock set because we want to give a set pulse in the right moment, and the other line is the right step. You see here is the last step, so is the 6th step where we go because it's the last operation, acquire the result in the register, in our case register 1. So we acquire the result in register 1 in step 6. Here is the stepper. We perform the ALU operation using step 4, 5 and 6. Basically in step 4, so as a first operation, we want to give we give a reg pulse. So in step 4 we enable register B to produce an enable pulse, and register B is here. So in the fourth step we have that this AND gates has this line selected, so high, the step line high, and when the enable pulse arrive, this give a pulse, a 1, and so the R1 register 1 receive an enable pulse, putting the byte on the bus. In the meantime, we give always step 4 and set pulse to the register TMP, to the temporary register, to acquire the content of register 1. And this is goes, sorry, to the temporary, so to our register here. So here we have the ALU, here we have the 4 registers and the accumulator and the temporary register. So that wire is connected with the set of the temporary register. So in step 4 we give an enable pulse to register 1 and a set pulse to the temporary register. In step 5, you see here, we go down, and in step 5 we enable all the opcode, because in step 5 we are going to perform the ALU operation. So we enable this, which is enabled also by the first bit of the instruction code. So in step 5 we have the opcode here, which is connected to the opcode input of the ALU. So we choose the operation we want to perform in step 5. Also in step 5 we give an enable pulse to reg A. So we put on the bus the other operand for the ALU. In our case is the register, the content of register 0, when the enable pulse arrive, of course. And also we give a set pulse to the accumulator to acquire, to store the result of the ALU operation in the accumulator. Step 4, 5, and 6 are enabled by the first bit of the ALU here. So the 0 bit, which defines the ALU operation, enable all this AND gate. In this way we are sure that this kind of operation are executed just when the ALU instruction code is right, so when is an ALU instruction. Otherwise all these AND gates are blocked. So now in step 5 we are have performed already the ALU operation. The result is in the accumulator. And so in the step 6 we give basically an enable pulse to the accumulator in the right moment with this AND gate connected to the clock E and to the step 6. So we put on the bus the content of the accumulator, so the result of our ALU instruction, and we give and set pulse to the right register, so to register B. So we go to register B, register B in our case is register 1. So in step 6 we have when clock set is high and step 6 is high, the first register line is high, so we give set pulse to register 1. And we acquire in register 1 the result of the ALU operation. The last thing I will have to describe is this logic here, and it is just 3 inputs AND gate connected with the opcode. When these are 1, 1, 1, the opcode, the AND gate is high, so the NOT gate, the output of the NOT gate is at 0, blocking this step 6, because when the opcode is 111 is a compare operation which doesn't need any storing in the register B, so doesn't need the acquisition of a byte in a register. Is just a comparison operation which we see in the A larger and equal bits of the ALU, and we don't need to store any result in the register. So this is just a logic to block the acquisition of the ALU output in the register. So now let's see a real simulation. So for example, we want to perform this instruction. So basically, this is, we can write it here. This is add R, the content of R0 to the content of R1 and put the result in R1. So this is the operation we want to perform. So now let's go here to register 0 and 1. So we can put the number 3 inside the register 0. We acquire it in this way. And the number, I don't know, 6 inside register 1. Okay. So let's see if we have done this. So we enable register 0 and there is the number 3. We enable register 1 and there is the number 6. So we expect at the end of our simulation that in register 1 there is the number 9, 6 plus 3. So let's see if it works. Let's see the timing diagram also. So I give a reset pulse to perform a cycle, and here we see our, okay. So here we see we have given basically a enable pulse to register 1, and we have put the content of register 1 on the bus with this enable pulse. This is the fourth step. And we also have given set pulse to TMP. So the content of register 1 has been stored in the temporary register. In the next step, we give an enable pulse to register 0 to put the content of R0 on the bus, and we give a set pulse to the accumulator, because this is the fifth step in which we perform the ALU instruction. And when we put the second operand in the bus, the ALU has both the operand in its inputs, and so we can perform the operation straight away, because it is a combinational circuit and it doesn't need any clock. So immediately the result is on the output of the ALU, and we give a set pulse to the accumulator, always in the fifth step. So at the end of the fifth step, the accumulator contains the result of the operation. In the sixth step, the last step, we give an enable pulse to the accumulator to put the result of the accumulator on the bus, and we give a set pulse to register 1 to acquire and store the result in the register 1. Okay, so the timing diagram is okay, and we see if there is the number 9 inside register 1. If everything worked, should be in this way. So we put with an enable pulse the content of register 1 on the bus, and we see here there is the number 9, because this is 1 and this means 8. 8 plus 1 is 9, and so the simulation worked. So let's see another simulation. For example, we can perform a NOT operation. So the code is 0, 1, 1. Of course, the first bit is at 1. And we choose the register 2 as reg A and the register 3 as reg B. So basically we are saying that the operation is this: note R2 and put the result in R3. So note the content of R2 and put the result in R3. So we acquire this in our instruction register, and we put some bit in register 2 and register 2. Basically, we want, for example, put these first 4 bits at 1 and the second at 0. And we put this inside the register 2 because we want to invert it. So here is the content. So in register 2, there is this byte here with the first 4 bits at 1 and the second at 0. Inside the register 3, we see what there is. There is a byte or 1. So at the end, I want in register 3 the opposite of register 2. Let's see if it works. So let's see if the bus is free. Okay, see, yes. Okay, I give a raised pulse here, so I perform just one cycle. Otherwise, I keep inverting, I don't understand the result. So just one cycle, you see, 1, 2, okay. Now we see below what there is inside register 3. So inside the register 3 should be 0, 0, 0 and 1, 1, 1. So the first bit at 0 and the second at 1 because it's the opposite. Let's see, register 3. Okay, it worked. Because this byte is the opposite of the byte in register 2, which is 1, 1, 1 and 0 at the end. Okay, it worked. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.